So good afternoon, everybody. This is going to be the second lecture for today. It's going to be about reinforcement learning. It's supposed to be an introductory lecture for this topic, which actually will be extended next Monday with a talk by Oriol Vinyals out here at UPC. So first, I'd like to acknowledge the help by Miriam Belvé, who's a PhD student of mine who dealt with this topic last year and from who I learned a lot. And also Serena Young from Stanford University. I basically took the structure of today's lecture from her class. So if you want to watch again and watch it from another perspective, I suggest that you just click on the video and you can see her class, which actually is extended. I'm just going to cover half of her class today in our lecture. This is the outline for today. I'm basically going to first explain what is reinforcement learning, what are the basic elements in one of these architectures, and what's different from the architecture we've seen so far on deep learning. Then I'm going to introduce what's a Markov decision process, which is the framework that allows us to formulate these kind of problems, and the elements and functions that they are defined from the Markov decision processes. And then we get into the deep learning part. So actually, it's not until point 4, until this fourth part, that deep learning gets into action. Okay, so what I mean is that reinforcement learning is a field of machine learning that has been quite successfully lately because of deep learning. But there are many solutions for deep reinforcement learning which are not based on deep learning. And then finally, just very briefly, I'll give you some pointers to some software frameworks that you might want to use if you want to get into this reinforcement learning world, and finally, many other pointers to learn more on this topic. So starting from the motivation, we can define reinforcement learning by a way of programming agents by reward and punishment without needing to specify how the task is to be achieved. So this is a definition from these authors from '96. And just notice that there are some new keywords that we hadn't seen so far. It talks about reward, and it talks about punishment, and it talks about agents, and tasks. Maybe we had thought about that, but these are like new terms that we hadn't seen yet on this course on deep learning. So the idea for today is that you get familiar to these topics and figure out how to integrate that with a deep learning framework. If you remember from my first lecture, when I introduced the perceptron, actually I started by showing this famous Jalekon's cake, the forest cake, where he referred to pure reinforcement learning as the cherry of that cake. So this means that that's a kind of machine learning from which we expect our system to learn with very, very, very little data. At least compared with other types of machine learning that exist. So far, you have mainly seen in this course solutions for supervised learning. So you have pairs of labels, and you want to estimate a function that, given some input data, will predict that label. So you want to estimate functions that make this mapping between input data to whatever output. And I think that Ramon actually mentioned the other day that there are big issues on that, because to do supervised learning, you need to have all these pairs of data and labels, and collecting that it's pretty hard. Yeah, and that's why nowadays there's many people who are actually exploring other venues for machine learning, especially on the unsupervised and predictive learning. That would be like where we have most of the data. So we just have raw data with no needs of labels. And you're going to have a lecture on this, I think, in 2 weeks. So you're going to have Santi Pascual talking about unsupervised learning and generative models. But today, I'm going to stick on the top one, on this one, on the cherry. So here you have what I just mentioned. You've seen this already. So the idea of the reinforcement learning, that's where we are going to discuss, is we will also want to estimate a function f that will generate some outputs y, but this function f will not. The goal will not be actually to predict y, but to solve something else, another charge. So actually, this other goal will be actually to maximize something we'll call a reward, but it's not actually that the reward is the output of f. Okay, so f will help us to move forward to get the best reward we can, but it will not directly give us the reward. That's a tricky part. So we focus about reinforcement learning, in opposite to the supervised learning that you have seen so far. Let's go through a basic architecture for reinforcement learning. And I'll start with this example. Maybe you've seen that. That's a network that is trained on reinforcement learning. So it's a machine that's playing this. It was named the Brick game, Arkanoid game. So the idea is that the control of this game is automatic, okay? And it has been trained with a reinforcement learning agent. So just notice that at first it doesn't play very well, and then it begins learning how to do it better, yeah? And the more training episodes, the agent, that's the name of the system that's taking control of the joystick, is playing better and better and better. Yeah, so now he's doing quite a good job. And after many more, you see how now that the system just becomes a pro, and actually it learns to put the ball on top. So that's maximum score with minimum effort, right? So maximum reward with minimum action, and that's what these systems are aimed to do. Yeah, and that's actually this example that you are seeing. It was kind of the beginning of this explosion of deep learning, deep reinforcement learning that we have, which is a sub explosion in the field of deep learning. This paper was published in Nature. Actually, I think it was published in Archive a year earlier or so, and it's actually what I just shown you, and it's the starting point of the company that Uriol Viñols will talk about next Monday, which is Google DeepMind, but I'll go back to the Google DeepMind in the future. By now, as I'm going to follow this example of video games, the basic example I'm going to follow is that we have some system that's called this DQN. I'll talk about it later, but it means Deep Q network, which is like the deep neural network that solves that task that I just presented. What it's doing, this network, it's just looking at the pixels, looking at the raw pixels, yeah, so screenshots of the screen, and then he's applying convolution operations, which you well know. It has some hidden layers, and in the end, this network, what it does, it predicts what action to take, yeah, and with the action, it moves the control of whatever player or sorry, whatever this can. I think it's a spaceship this time on the game, yeah. So that's the example I'm going to follow just to explain the architecture, which is coming next. So let's go for the architecture. So in this example of a video game, so we have a game console. So probably most of you don't even know what it's that, but that's a video game console. Yeah. So that's the very beginning when I was playing video games when I was a kid. That's the first one that I play with, an Atari video game. So Atari is an American company which no longer exists apart from marketing issues, I think. But it's a very nice brand. But at that point, they did video games. That was the video console. And that's in the field of reinforcement learning. That's called the environment. Yeah. So the environment, it's this computer that it's, in our case, it's generating this virtual world. In our case, in the case of the video game, that generates and controls this world. Then, what does the environment provide? So the first thing that the environment provides is a state, yeah, and the state in this case of the video games are the pixels. So the image that it's shown on screen, that's the state. And as the pixels they evolve in time, this state depends on time. So that's why there's a ST here. Yeah. So raw pixels in this example is the state. So in classic video game playing, so when humans play with the video games, there's a human that will be looking at those pixels. And in the reinforcement learning framework, this human that will take decisions is called the agent, right? And actually, that's the part that we want to simulate because it's a machine learning course, right? So this agent just looks at the state, and based on whatever policy, actually that's something called policy that I'm going to talk later. So based on some policy, it will take a decision on which action to take. And in the case of video games, the action is just to move the joystick. And of course, the action will change in time. So when you play video games, you do take different actions based on the different state that you see. This action gets back to the computer, to the environment. And the environment, depending on the action, it will issue some reward to the agent or not. Okay, or maybe it will be a penalty, right? And so in such a way, that will be how the agent will learn how to play video games. That's actually what probably all of you have done when you play video games. At the beginning, you really don't play well at all, but based on the rewards that the system gives you, you learn how to play. First thing we must notice here is that this reward is given after the agent takes an action, yeah, and which is also a bit different from what we have seen so far, because actually you get the reward after your explore. It's closer to real life, but it's not that close to what we have seen so far in this course. And also based on the action, so apart from the environment, apart from issuing a reward or not to the agent, the environment will also update the state. So it will probably somehow will change the state of its state, and this state can be influenced by the actions of the agent. And then the cycle just goes on and on and on, and that's how the formality of the reinforcement learning wall is formulated. The goal for the agent is to complete the game in this case, to complete the game with the highest score, and so that's how we learn to play video games, and that's how the system I show learn to play as well. Another way of formulating this goal is that the agent must learn how to take actions that will maximize the accumulative reward. So what I mean with accumulative reward is that in this video game, the point is to get the highest score at the end of the game. Okay, it's not at 10 seconds or 20 seconds or 30 seconds, not at that specific moment, right? You want to have the score at the very end. And that's what makes things quite challenging, right? Because probably that requires some planning. So when we had the brick thing, so first you maybe at the short term, digging a hole on the side of the bricks, maybe that's not the optimal way to, at that point, to get the highest reward. But in the long term, that's the best option, right? And that's what makes things a bit more tricky as well with reinforcement learning, because the reward is actually the accumulative, like the one that will, the one at the very end, the one that you accumulate after playing the whole game, not just that in the middle. There have been, as I mentioned earlier, reinforcement learning has been out there for a long time. There are many other problems that have been formulated as reinforcement learning problems. Other ones, like, for example, this one is quite classic. That's called the cart pole problem. And in this case, the problem is you have an oscillating pole on a moving cart. And the goal is to pushing the cart horizontally to keep the pole like vertical. Yeah, that's the goal of the problem. And again, this can be formulated as an agent environment that interact. For example, the environment, in this case, will provide as a state the angle, the angular speed, the position, or the horizontal velocity of the cart. Then the agent can, as I said, that it can apply force horizontally on the card in each side. And if you want to train a system to do that, one solution that you could have is to provide +1 reward, just 1 coin or whatever, 1 unit of reward, every time that the pole is upright. So if you do that, you might manage to train an agent that will actually learn that as he will try to maximize the reward, he'll try to keep the pole as vertical as possible. Another option, which is much more modern, would be just to have a robot to move around. In this case, in this example, I think that's also from, I can't remember, from OpenAI, I think, and Berkeley. That's the goal is to have a robot to move forward. And in this case, so that could be the robot. What you do is instead of building a real robot that might break, right, or all the mechanical issues, what you do is you build a virtual environment, and then you train your agent in a virtual environment. That's very common in reinforcement learning. Yeah, instead of, I mean, maybe in the end you will build the robot, but if you want to train it for, you want to do something virtual, because then you have like infinite simulations for free, or at least much cheaper. So in this case, what will be the state? The state could be the angle and the position of the joints of this robot, and you have the the environment just tells you what's the angle. The agent applies torques on the joints, so it can control all torques of the joints. And again, if we want this robot to walk forward, you want the robot to be upright and to move forward. Yeah, that's what we like to do. And I'll show you a video of how this robot evolves. So beginning, it's really bad. Yeah. But after some iterations, just by giving the reward, okay, just a few more iterations, by giving rewards to the robot, it manages to do what we want to, right? To move forward. Okay. So, very impressive. Just notice that in this case, there is nobody programming. Nobody programmed what the joints had to do. Okay, that's another robot they have. It's like a spider, and again, the goal is the same one, right? And here again, the trick is that nobody is really thinking, oh, you must move this joint, and after this one, then the other one. No, just say, okay, if you move forward and you are bright, you get a reward. If not, you don't get it, and you just let the system to learn the complexity of the system, the complexity of the joints, because that's, of course, that requires some coordination, right? So that's pretty. If you want to program that manually, that will be pretty scratch. Okay. I guess he's trying to stand up right now. Yeah. So let's go to the not so fun part, which are the equations that govern all these control systems. So the framework to formulate reinforcement learning problems are Markov decision processes. Probably you are familiar with them. And here the basic assumption is that the current state completely characterizes the state of the world. You don't care about what will happen in the past or in the future. Just the current state, it's enough for you to characterize everything in the world, which is kind of the opposite of what Marta just explained, where he explained networks that had memory, that actually the memory was important. In this case, like at that time, that's all you need to know about the world to solve this problem. That's of course, that simplification, but probably that's enough for this problem. Then we're going to use the following notation. We're going to call S as the set of all possible states. So again, I'll follow the story of the video game. So in our case, the S would be all possible screens that could be painted by the console. Yeah. So all possible configurations of invaders and spaceships and shots, all of them. That's the whole set of S. A is the set of possible actions. So classically, at least in this game, as far as I remember, it was right, left, and button, which was to shoot, as far as I remember. Maybe there was something else. Then R is a distribution of rewards given a pair of a state of action, right? So given an action, you can kind of have some different rewards, and you can estimate that. P will encode the transition probability. So this means the distribution over the next state given a state action pair. So if you are looking at the screen at that point and you take an action, how to model which are the new steps that you can go to, which could be more than one, depends on what the video game, how it's coded, how the environment will evolve. And then finally there's this gamma that's called a discount factor. That's going to be very useful because in many cases, so apart from the agent, apart from aiming at having the highest cumulative reward, trying to get the highest score in the video game, what we will want as well is to reach there as soon as possible. Yeah. So at the beginning with the bricks that you put the ball on top to have the highest score very, very quickly. Yeah. So if we want to do it quickly, we need some factor there that will tell us that if we take more steps, that's bad. That's going to penalize us. And that's what this gamma will be modeling. You'll see it now in the next equations. Yeah, but it will kind of penalizing. It's a discount factor that will force the agent to solve the task in as quickly as possible, or achieving the highest reward as quick as possible. So in a Markov decision process, what we have is at start, there's a sampling for initial state, whatever screen. Then the agent selects an action. And based on the action, the environment will select a new state. So that will be looping. And also based on the action, the environment will provide a reward. Here, the key, and actually what we want, so that the key to all this system, what we want to solve is to provide what's called a policy to the agent. So that's like some guidelines, some instructions for the agent to know which are the actions to take to maximize the reward at the very end. Yeah, the key name is policy, and it's modeled by P. And this poly allows the agent to choose an action based on a certain state, and it's a Markov decision process. Like as based with the current state, that's all we need to know. So that's what the agent will need to apply the policy. So now with this word policy that I have introduced, I can reformulate the previous goal. We had the previous goal that we want the agent to learn how to take actions to maximize the reward. Now with this MDP formality, now what we want is to find a policy, optimal. So this star here will mean like the optimal policy that maximizes the cumulative discounted reward. So okay, so now here you have the RT is the rewards. That's remember that the RT is the reward at each time step. But then you have this gamma that was a discount reward. Discount factor, which actually what it does is that it will kind of decrease the reward in time. So gamma could be smaller than 1. Yeah. So the longer it takes, so the more time steps we take, this factor will be smaller. So this will make the reward that you get from that time step to lose value, right? This will force to have rewards as quickly as possible. there are there's this problem, which is also very classic in reinforcement learning architecture. That's called the grid wall. It will allow me just to explain a little bit about states and actions. Okay, it's just an intermediate step before going forward with the formulas. In this grid wall problem, the goal is to reach one of the terminal states. So that's the one re-out, the ones with the star, in the least number of actions. Yeah. If you want to solve the problem, just notice that so each of the cells in the grid is a state, and so here it is. So each of the cells in the grid is a state. That's what the environment describes. And then the agent can take different actions. It can move right, left, up, or down. So the agent is in some state, or is observing some state, and then it will take some action to solve the task, which in this case is to go to a terminal node. The way to train a system to solve this task will be to provide a negative reward for each transition. So actually, in this case, what the reward is, the reward that we provide will just directly force the agent or push the agent to go as quickly as possible to the terminal node. That will not. The agent will have a penalty if it just goes walking around without reaching the terminal node. Yeah, so you will force the agent to go to the terminal node. If we consider, so just remember that the way the instructions that the agent or the criteria that the agent follows to solve the task, it's what's called the policy. Yeah? Now here we have an example of something called a random policy. Random policy will be like in every state. So for each of the cells in the grid, you take one action in a random manner, and that's how I represent here with the arrows. And of course, that will not. I guess that all of you should be aware that this is not the way to have the highest reward. Yeah, because you'll be just, well, I mean, you might end up in a terminal node, but that's probably not going. You will not get the highest reward possible. Yeah, so that's the random policy. In this case, is not the optimal policy. Yeah. So what would be the optimal policy? That's for you to think now. So I'll give you 1 minute to decide the optimal policy to solve this problem. What you have to do? What you have to do is to consider each and every state and draw with arrows, right, left, up, down, which are the actions that will be considered in the optimal policy. There might be more than one. Okay, so some states have more than one actions that are part of the optimal policy. Yeah, so I'd like you to solve this now. I'll give you 1 minute. Do you have paper? Or if no, you don't have paper anymore. Well, if you have paper, you can solve it. If not, you think about it or discuss with your colleagues. No. So the goal is, if you are in a state and you want to reach one terminal state, but in as few steps as possible. So just to get the highest reward possible. So every time you take a step, every time you get a step, you get a penalty. Let's say. Okay. So you want to take as few steps as possible, but you can reach any of the two terminals. You never mind which of the two. Yeah. So you must think, okay, if I'm here, what actions are part of the optimal policy if I'm here? Then you draw them, and then you say, okay. But if I'm in state here, which are the actions that are part of the optimal policy? And just consider that for each possible state. Yeah, one state is one cell, and you think which actions are part of the optimal policy. And in one state, there can be more than one action. Okay. Yeah. So don't know if you have solved everything, but at least you've had time enough to think about if the problem is easy or difficult or nonsense or it does. So that would be the solution you should have come out more or less. Yeah. So you see that if in some of the states it's quite obvious, especially for the neighboring ones. Maybe in some other states this one. From here you need 2 steps to reach one of the terminal options. So that's 1, 2, 1, 2, and that's it. Just notice that given a state there can be more than one actions that take you to the highest reward, highest cumulative reward. Okay, and that's the kind of problems that we want the agent to solve. Yeah. So just imagine that you need to program an agent that needs to solve this. Yeah, and just notice the challenge that for given a state there might be more than one option. And okay, that was kind of an easy problem because at least here, the stars are not moving, and when you do an action, that's not changing where the stars are. But if they were moving, that things will get more complicated. Okay, so now that you know what the optimal policy is, so the optimal policy is for this problem is this, right? So the actions that take you to the maximum cumulative reward. And in that case, it's kind of easy, but some others are really not that obvious to solve. How can we formulate the finding of the optimal policy? So as there are some randomness, like we saw, for example, that the agent in the previous example, it could take different actions going into the best direction, but there of course in the states there can be many different states, like the computer when it generates the pixels, when it simulates the game, it can take different decisions that we are not aware. Yeah. Then as there's some randomness there, we'll need to deal with expected sum of rewards because we don't have a certainty of what's going to happen. So what we'll say is that the optimal policy is the policy that will maximize the expected cumulative discounted reward. That's the basic criteria to choose the optimal policy, and now we will develop from here. Okay, I give you a few definitions now, and now I'll go back to how to explain how to find the optimal policy. Right. First, this definition. That's the value function. The value function tells you how good a state S is for a given policy pi. So you have here that this value function is the expected cumulative reward from following the policy pi from state S. That's this V value function. Is expected, and it's the cumulative reward. So you have all the rewards with a discount factor, considering that we're starting from this current state and following this policy. Yeah. So this V tells you how good the state is for a given policy. Another definition, it's the Q value function. So this is just the value function. It only considers the state. But if you consider pairs of state and actions, then what you have is a Q value function. And in this case, the definition is very similar to the previous one. The Q value function tells the expected cumulative reward from taking action A and state S, and then following the policy pi. Yeah, so you have the expected cumulative reward, and it's like the starting from this state and this action and following policy pi. So if now we so that's if Q is the expected cumulative reward, and we want to have the maximum amount of reward, actually what we would like to know is how can we find the optimal Q value function at state S and action A. There's a missing A here. So that's what we would like to find. So given a pair of state and action, what's the policy that we want that we should take to have the maximum expected cumulative reward? What we're going to do is we're going to choose the policy that maximizes this expected value. In order to formulate this process of choosing the policy that maximizes this cumulative reward, we are going to use something called a Bellman equation. That's a well-known equation for control systems. And basically, what this equation presents is that the maximum expected cumulative reward for starting from this pair, it's part of the reward that we get. So it's an expectation across all possible future states, which is kind of a way of introducing the randomness. But it's a function from the reward that you get from the considered state and action, and also from the maximum expected cumulative reward for the future states. So actually, you kind of say like the best that I can get from this state and action is the best cumulative reward is the reward that I have now, and the best reward that I can have considering the future, the possible future state and actions. That's kind of the way of how this equation works. So now, if we want to find the policy that maximizes this discounted reward, actually, so this is the same equation, okay? Right? I'm just highlighting different things. So it's the same equation. It's still the Bellman equation, but just notice that if you want to achieve the maximized cumulative discounted reward, what you're going to take are the actions that maximizes also the expected cumulative reward in the future, which is kind of a bit obvious, but that's how the formalism works. So as this is going to maximize the value, we can. So just remember that we reach here as formulating trying to find the maximum policy. So in the end, what it tells us is that the optimal policy corresponds to taking the best action in any state according to this function, this Q value function. The problem here is how to estimate this Q, yeah, because estimating, so this Q function, like given a state and action, tell me what's the best reward I can get. That's okay. How do you estimate that? That's very complicated, right? And one way to do it, it's something called the value iteration algorithm, which basically what you do is you do it in an iterative way. So you will try to estimate this Q function at different in an iterative way. Yeah. So I, in this case, it means that we are trying to estimate this Q function. And the idea is that if we are able to iteratively estimate this Q function in an iterative manner, and we iterate until infinity, this estimation will match the actual optimal Q value. So doing that, so trying to really estimate all possible, so trying to estimate the cumulative reward for all the possible state and action pairs. That's actually it's a good formalism, but in practice that's not something that you can do, at least in these kind of problems where we are dealing with a huge amount of possible states. So maybe the actions, they might be the joysticks, but the states are huge. And if you would like to estimate the maximum cumulative reward for every possible state, every possible pair of state and action, that's huge. So remember that in this case, a state is the configuration of pixels. So all the screens shots, let's say, that the computer console can generate. This means that you need to, the field to explore is huge, right? So in this case, this approach is not scalable. And that's when deep learning comes to the rescue, because the trick here is to train a network. These parameters here are the parameters from a neural network that will actually estimate this Q function, right? So if we can train a network capable of approximating this function, then we'll be able to estimate the cumulative reward for every pair of state and action, and as we in the end will take the actions that maximize this Q value, this Q function, then we'll be able to take decisions for our agent. And that's what deep Q networks do, and that's the revolution in deep learning for this kind of task. So now we're going to get into details with this how deep neural networks are applied in this context. That's called deep Q learning. That's the okay. So what could we do if we had a? So remember that our problem is that we want to estimate this function, this an estimation of the Bellman equation, approximation of it. We'll need to have is to train a network that given whatever state and action. Here there's more than one state because in the paper from that presented this DQN, what they did is instead of showing only one frame, they show the 4 frames for the last 4 frames of the video game. Okay, but you can consider it's one state. So you have a state and action. You allow the network to predict the Q value. How can you do that? We can formulate that with a loss function where we are going to we want to have a network. So that's the neural network. The function we want to approximate. It's over here, and we want it to approximate the Bellman equation. That would be like the Bellman equation as we are doing it in an iterative manner. So we have the parameters of the network in previous state. So we want to train a network that will, in the end, approximate the Bellman equation. That's what we have here. And that's, again, the same. Just notice that to train a network that will approximate the Bellman equation, during training, it will be necessary to compute the reward for the current state action. Yeah, that will need to be done. So this means that if you really want to train a network that estimates the maximal reward that you want to obtain for each state, you actually will need to have the video game playing and giving you the rewards, so you can actually put it here in the equation and compute the loss function. Okay, this function is differentiable, so here you have the gradients if you want to take a look at it. And that's how, so we have everything. We have the loss function, we have the gradients for the gradient update for the backward pass. That's already integrated in the frameworks that you can use. And actually, while this would be what I explained so far, if you look at the paper that proposed this work, they did something slightly different. So they did the following. What they did is, instead of having a network that you have as input the state and all possible actions, like the screen and joystick up, a screen, joystick down, a screen, joystick left, right, whatever. What it is they just put the state as the input, so the screenshot, actually like 4 screenshots. And in the output, they predicted the Q value for each of the different actions to be considered. Yeah, and this way, so what they have the screenshots, they pick the Q value for the different actions, and what they will actually, when you play, what you choose is the Q value which is higher. The highest Q value is the action that you actually take when you are training the system, or when you're playing, right? Maybe when you train you do other things, but at least when you're actually playing. And you did this also in only one single feed-forward pass, right? Because if you did the other approach, you would need to have a feed-forward pass for each of the different actions, for each of the joystick movements. So that's a network that they design, or one of them. I think they designed because they play with different Atari games. That's one of them. Again, as I show later, they had convolutions, they had ReLU activations, convolutions, fully connected layers, and in the end, they predicted the Q values for the different actions. In this case, the actions were the joystick moves, and joystick move combined with the press button. So the number of actions range from 4 to 18, depending on the video game, because they played that for different Atari video games. Here you have the details of one of the networks where the output is, there are four actions. And here, and again, I mentioned this thing of the 4 frames. If you train one of these systems, there's a very good practice to follow, which is something called the experience replay. So I'm going to mention that whether it's, I guess that if it's a deep learning system, it's more important. Which is that if you try to train one of these networks with consecutive samples, so you have your system playing the game and you go training your network, you will have problems because your samples, which are consecutive, they are quite similar and they might be correlated. And also, as actually the next samples, so next observations of state and action that you show to the network, they are conditions from your previous actions. It may happen that maybe your network have a bias to move the joystick always to the right, yeah, and then it kind of if in the past you move the joystick to the right, then in the future it might have the bias to move it there, and in the end you will not have samples of what happened if I move the joystick to the left, which might be also useful because maybe then you learn a better policy. So it's important that to solve these problems, you introduce this thing called experience replay, which actually what you do is, okay, you have your system playing the video game, and first you store the observations that you have. So you save, you record what you did. So you have a memory table where you store the transitions that you have and the rewards. And so that's what it plays. But then when you train, you don't train sequential actions, state action sequences, but you just you choose your samples randomly. And then you create mini batches to train your network this way. So you go to your memory table, you take some random samples, and that's how you train your network. And then you let it play, you'll get more samples, you store them on your memory. And again, and for training, you take some more new samples and you train again. Yeah, so that's quite very important. Otherwise, you will have problems to train your network. So if you want to see how one of these systems works, you can click on this link, I think, and it runs reinforcement learning in your browser. Also, I'd like to mention one of the work that we had here with Miriam Belvé. So now it's more about some examples. So this example, what we did here at UPC was to have a reinforcement learning agent that was able to locate an object on an image by doing zooms. Yeah, so we have the image, we zoom in one area of the image, and then we zoom again, and then we zoom again. So in the end, we found the object. And in this case, our state was the the features from the convolutional layer of the region that we had cropped because we were like zooming in. Yes, that would be the state. It was changing. So actually, we took two architectures. So you should look at this one. When we did the zoom, so of course, every time you zoom, the features on the convolutional layer they change. So the state was changing. And then in our case, we also use something called a history vector. That's quite common as well. So when you have this will be the Q network in the end that takes the decision on where to zoom. But so we have our visual features here from the image, but we concatenated another feature over here, which is the history vector, which is a way of introducing memory. Yeah. So again, now going back to the lecture from Marta was already presented a network that naturally introduced memory, and actually in the recurrent neural networks, you don't have to tell them how big your memory should be. In our case, in this network that we built, we actually chose, I think it was a size, I think it was size 6, but I'm not really sure. So or maybe it's 24. Maybe 24. So we save the previous decision that we took, okay, for a fixed window length, and that helps as well. So we define rewards based on how well our zoom was matching the object. So because the goal was to find the object in, and then that's the kind of movements that we have. So you have here, this was a plane. We had different, instead of allowing the system to go around widely, we also just only provide some 1, 2, 3, 4, 5 possible actions to zoom center or zoom in the 4 corners, and a final action, which would be the blue, to say, okay, I found the object. That would be the trigger action. And that's one of the examples that we have where we see that the agent learned to focus on the objects. If you want to play with it, you can just click here, and there's the source code there. Yeah?
When you introduce memory, isn't that like not assuming anymore that future states only depend on the current one?
Yeah. Yeah, that's a way. It's quite a common practice to do it, but it seems to help the system to train better. Okay, just to finish now about if you want to play with reinforcement learning, there are some frameworks, software frameworks that you can play with. One of them is called OpenAI Gym. OpenAI is a kind of a big non-profit company with one of the most famous one in reinforcement learning, and they have an environment there to train reinforcement learning agents. And there's a connector with Keras that helps using this package from Keras. It's called Keras RL. Actually, OpenAI has another framework called Universe, where they have plenty of video games, and you can train your agents to play against them. If you want to learn more, here there are some introductory videos to show your family, I guess, and friends, because they are like very friendly. This is a series, Deep Learning TV. There's a series of very friendly videos that will give you an overview of deep learning. And Sirai Raval is one of the most famous YouTuber on deep learning. How many of you know him? Okay, great, good job. So he's a celebrity. You know him probably better than me. Then if you want other people who are famous but not YouTubers, there's this course from Stanford, all in reinforcement learning. So here we'll give you 2 hours and a half of reinforcement learning. So, but there are like just courses on reinforcement learning. So it's been a very long and extensive research field. This is one from David Silver, from Nando de Freitas. Actually, there are some lectures when he was in Oxford. Peter Avil and John Schulman from Berkeley and OpenAI. Also, I would suggest that you look at these kind of algorithms, the autocritic algorithms. I didn't have time to go through them, but they are also quite important. Evolutionary strategies. And that's it for now. Just final idea, just remember, I hope that at least now, if you didn't get lost from the equation, that you have an idea that reinforcement learning is another way for doing machine learning, that it has some particularities compared to supervised learning, also compared to unsupervised, but you haven't done unsupervised yet, so it's more difficult for you to see the difference, but you'll see it when Santi explains it. And in this case, there's no supervision. Feedback is delayed, so you want to maximize the final reward, not the instantaneous one. And time really matters, so there's a sequence of actions. So coming next, on Monday, you have a Supermaster lecture. I'll give you just a very brief introduction to this lecture. So this DQ network from Atari Games that I presented, actually it was developed by some researchers in London, some English researchers, who did this nice work under a company called DeepMind. And after doing this work, the company was acquired by Google for £100 million. Then you can see 2014. And they are the creators of many very nice works, like probably you've seen this work from AlphaGo, which is this computer that has beaten the best humans playing this Go game, which is super complicated, requires very long-term planning. There's a movie, documentary. I'm not really sure if it has been released here. Has anybody seen that? No? Okay, so we'll ask Uriol if we can watch it somehow. But it was released last spring, I think. They have, Uriol will talk a lot about StarCraft 2, so probably many of you know about that. So that's a video game that also requires a lot of planning. He's a big fan of it, so now he has a framework to train reinforcement learning agents to play StarCraft 2, and he will tell you about the details. So next Monday, you should have registered online. So we're going to be many more people than what we are now here. So we just had to change twice rooms. So first it was in Aula Master, the talk. It's not any longer in Aula Master, okay? Then it was in the Sala de Actas in IFC Vertex for 160 people. It's not any longer in Sala de Actas. So the next room that we have is L'Auditori in Vertex. That's for 477 people. I hope that everybody can take a seat there. Right now we have like 200 registered people. So feel free to, now we have seats, so feel free to promote between your friends and colleagues. I think it's going to be a very nice talk. So there's going to be an introduction by Yanis Kalantidis from Facebook Research. It's going to be a short one that will explain just how Facebook is using these technologies that we are presenting in this course in their work. And then it's going to be like the big lecture from Uriol Viñals on reinforcement learning and DeepMind and something else, which I'm not really sure. Okay, so see you there on Monday. But now we have a break and we talk about the project, so you stay here. Okay, take a 10 minutes break.